Okay, let's get started. Our afternoon session will be focusing on the Agile Hardware design. Our first speaker is Mark Horowitz from Stanford. Mark is someone who doesn't need much introduction, and he specifically requests that I shouldn't talk too much about him. So let's get started and think about how we can learn from Mark about Agile Hardware design.
Thank you so much. All right, so I was debating about which of two talks to give you, and I only had 20 minutes. So I'm gonna give you kind of two talks. The first talk is a brief overview of the research going on at Stanford, and I think the second part of the talk is a little bit about what I think the opportunities, I won't call challenges, the opportunities for Agile design. So I just want to start off in saying that the work I'm presenting is not really work that I did, it's rather a work that my collaborators have done at Stanford. So I've been fortunate to be working on this project with Pat Hanrahan, Clark Barrett, Kayvon Fatalanian, and Priyanka Raina. And they are an amazing group of people, and it's been just amazingly fun to learn from all my colleagues. If you're thinking about trying to do Agile hardware, I think the first thing that we have to do is we have to avoid some common pitfalls that people fall into. And the first one I'll call the specialized hardware mistake, and the second one I'll call safe computing. And the specialized hardware mistake is very common because it's actually what we teach people to do in architecture classes. So, if you take an architecture class and you want to build an accelerator, just like Vivian talked about, what do? The first thing you do is you study the application, right? So if we're trying to do some image recognition, we'd study that application. After we study the application and we think about it, we change the application a little bit, and then we start basically designing the hardware. And then when we finish designing the hardware, we write the software. And of course, when we write the software, the first thing you have to do is write the runtime and maybe the compilers that you need for your thing. And then after you build that code, then you have to actually build the application code that goes on top. Now, as I think Dave Patterson said this morning, that is the waterfall model design. And this is a model of design that was proposed for software a long time ago, but we've moved away. And if you think about the large cost of designing hardware, and one of the things we're trying to address in Agile hardware design is one of the big costs is the software for that system, and we haven't addressed that at all. Now, of course, the specialized hardware mistake doesn't mean it doesn't work. It can be made to work. It just has a couple well-known downsides, which is it costs a lot of money, and it takes a lot of time to actually implement. And this is especially problematic because we all know the only software that works is the software you actually use. All software that you develop, when you first develop it, is crap. And I know that even in your big company, you're building this new accelerator, the people writing the software to deliver is on the existing hardware, so your software chain is not going to be as good as the ones that people actually use. The other problem is that when you build a new piece of accelerator, to port applications for that accelerator, because again, as Vivian said, you have to tune that thing for the accelerator, requires information both about the accelerator architecture and the application, and that is in scarce supply. So if the way we teach everybody to do this is not the Agile way, what can we do? Is there another way around this? And I make a joke that if we're talking about adding small additions to complex things, we're talking about adding cup holders. That's a whole different talk. Come talk to me later if you don't understand what I'm talking about. But basically it means that the systems you're working on and the applications probably exist already. So how do you manage to improve hardware and software while maintaining this end-to-end flow, which I think is really important if you're trying to do Agile design? We've seen this problem before and we've dealt with it successfully for a couple decades. We have applications and we have architecture, and you know what we did, right? We put in an isolation layer called an ISA that allowed software and tools to compile to that ISA and allowed hardware people to basically then innovate under that ISA. So the question is, can we basically do that in an area of sort of accelerator-driven design? This is where we have to not fall into the second common problem, which is the safe computing problem. Look, accelerators only can accelerate a very small class of applications. The only thing hardware does well is do things in parallel and exploit locality. If your application has neither parallelism or locality, just give it up. The accelerator's not going to help. You're going to all be limited by your memory system. So if I'm looking for a new ISA for accelerators, I'm looking for an ISA that nicely describes things that have locality and parallelism. Okay? And that's not hard to find. A universal new ISA or new abstraction is hard. That's not hard. Everybody who's doing this class always talks about data flow models, and we have 12 zillion different data flow models that people use. Let's just admit that we need a data flow model, and then what we can do is we can map our applications into a data flow model and then map the data flow model into hardware. So if we're going to try to do this agile hardware design, I think we're talking about something that maintains an end-to-end flow that's incremental and basically tries to improve both the application and the underlying hardware, and has some interfaces, clean interfaces that allows simultaneous development. Okay, so we're trying to do this at Stanford. We believe in order to maintain this end-to-end flow, we need applications that are written in a domain-specific language so that we have higher or more information about what that application is doing than just an implementation in C. We need a compiler to map this into this abstraction, to this basically hardware data flow, and then we need a way of mapping that hardware data flow into actual hardware. So in the particular project we're doing, we're using Halide, which is a language for dense linear algebra and for image processing. We have created a data flow representation called CoreIR that has formal semantics, so we can do a lot of proving and validation work on this level. And we decided that our target architecture is going to be a CGRA, a coarse-grained reconfigurable architecture, sort of a step up from an FPGA. I can talk longer about why we chose all these things. Halide, the real reason we like Halide is it's separated out the notion of a schedule from function. And the fact that the schedule is explicit allows you much more easily to re-implement your application for different hardware and different hardware constraints. And that's essential if you're trying to quickly map something to different hardware. It also exists as an open source standard, so we get to leverage that. We chose CoreIR because we needed something that was a data flow representation. It was constructed to have formal semantics, and it represents things as a DAG of operations. I will say that in talking to my colleagues across the country, everybody has their own data flow IR that they're using, and maybe we could get together and sort of standardize one, because I don't think we need 12 different ones. Now, why did we choose a CGRA? Well, it's universal. That means I wanted something that I could build an end-to-end system to, and I wanted to make that as easy as possible because I needed to build that end-to-end system. So the fact that it's universal makes it much easier for us to build the first working system. And it turns out to be, for doing data parallel applications, is a better target than an FPGA, although if I was Xilinx, I would have just used an FPGA because building a whole set of tools is not, and building a whole new platform is not easy. Of course, once you have a programmable substrate rather than the specific thing you want, there's an overhead that was mentioned earlier. We did some studies a couple years ago to look at what the difference between a programmable substrate and a non-programmable substrate was, and we looked at SIMD machines and CGRAs and FPGAs and other things. And there's about an order of magnitude in both energy per operation and area per operation that you lose when you go to a programmable substrate. And that loss doesn't depend very much on what substrate you choose, but if you just compile things, it's usually much better. So given this cost, why did we do this? Well, again, if I'm interested in an agile approach, I need to have a framework that's in existence that I can use and use to optimize my hardware. So it has to be basically universal to begin with. Otherwise, I'm developing this, the compiler is going to take me forever. And if you change the application, it might not work. But we chose this because it's a spatial architecture, and since most accelerators are spatial architectures, we thought we could incrementally then change the CGRA into something that's more accelerator-like, make it less general, or make it optimized for particular classes of things. And so that's the research that we're doing. Although first we have to build the end-to-end system, which is what we're working on now. Okay, so we have a working tool chain. I'm not going to bore you with this, but we can take image things and generate CGRAs out. Okay, we started this program a little over 2 years ago, maybe-ish. Last year, we taped out a chip. The good news is the chip worked. The bad news was that Not unsurprisingly, the first time you do something, you don't do it in exactly the best way. And we realized the whole structure we used to generate our chip was actually didn't have the right interfaces. And so we're now building the second generation of the chip. So what I'm going to do now, in the remaining 10 minutes of my talk, is to talk about the opportunities and how we're addressing some of the opportunities, but these opportunities are big opportunities. There's lots of potential approaches. So the first opportunity is the fact that nobody cares about your accelerator. You're building an accelerator, you're building this hardware, you really love your piece of hardware, but that's not going to sell a product. People care about solutions to end applications, and they care about how their application runs. And their application depends on more than your accelerator, it depends on lots of other things. And so if you build a whole Agile system for designing hardware, it's going to be useless because it's not going to address the user's problem. You actually have to build a system constructor, okay? And so all Agile hardware has to be in the context of a system constructor because you have to be able to take an end user application and demonstrate what it does in the end user application. And there's a huge opportunity here because we're not really thinking about that. Okay, for us, what we're thinking about is to deal with that, we are building an SoC and we're thinking about having a Halide application, which is a user application, and we're working for doing that all the way down to the accelerator and all the OS and other interfaces that need to be there. But one thing that comes up is when you're doing this, if you're maintaining an end-to-end flow, if you change anything in the flow, all the other tools in the flow have got to know about that change. Because there's something that's mapping the data flow graph onto the hardware. If the hardware changes, that data flow graph mapper has to change, right? Does that make sense? Okay, so the reason we had to refactor our design is when we started off, our first system had kind of two constructors. There was something that mapped applications and something that created the CGRA. And yes, there was a set up here of the, oops. There configuration data that was placed to the mapping system and everything else should have worked. But because we were using hardware generators, the way we did that configuration generation was just a different piece of the code. So we wrote the hardware, and then we wrote the generator that did the collateral, right? Because we're smart, we knew we needed the collateral. But then the consistency between that generator, between two parts of the generator, was not guaranteed. Okay, so one of the things that we believe is that if you're really thinking about this end-to-end flow, and you're thinking about how the software and hardware is going to be, you really need to have a system where the important information is encoded within the generator in a way that can be interpreted for all the different uses of that information. Right? So it's not sufficient to write a generator that generates the hardware and then spits out some text files for the next thing. The thing that generates the hardware has to be interpretable by some other agent in which to generate the collateral that you're going to need, because otherwise it's going to get out of sync and it's going to lead to some bugs that are really hard to find, trust me. So we came up with this notion that Pat Hanrahan came up with as a single source of truth, just because, in literature and humanities, there's no single source of truth. So we thought it was a little bit of tongue-in-cheek play. But the idea is we want a description of our hardware objects that doesn't just generate the RTL that we show, but can generate things for the mapper, can generate things for the functional models that you have to do, can generate things for the tests. So that we have one source of information about what this object is supposed to do, and can be used in other places. In order to do that, we believe we need to have those generators as actually being DSLs. So you encode that information in a domain-specific language that can then be interpreted by other agents that can pull these other views. So that leads to this notion that we need DSLs, not generic generators. And that doesn't mean that we can't use the generator technology that's out there. I'm all in favor of generators, but I think we really need to maintain end-to-end systems. We need something more than that. Okay, so again, from Pat, he has this notion that core IR is basically the base. Then there's Magma that goes around the core IR, which is kind of the constructor that we're using. Pat likes to say it's chisel for people who like Python better than Scala, but it's just a generator. But then on top of that, we have higher level DSLs. And in our particular thing, we have Peak, which is the processing units that we're building. We have Lake, which builds the different kinds of memory structures we have. And then we have Canal, which connects the data stores to each other and to the processors. Okay, So the second opportunity that we need to address is the fact that hardware design is more than just about functionality. So when you talk about software design, you're worried about the function. When you get the function right, that's okay. But we have timing. Anybody who's built hardware knows about timing closure. You know about layout issues. You know about the test generation. You know about scan and a whole bunch of other things that you have to do in any real piece of hardware. If we try to put all those issues into one generator, what you're going to get is you're going to get this thing that is unintelligible because it has all these things that the person who's looking at it has no idea what's going on. So in order to solve that challenge, what we're doing is we're trying to do a separation of concerns. And in our constructors, what we're trying to do is we build a constructor. Those constructors initially have information about the logical view, because that's what the designer's doing. And then we have passes that operate on those constructors or the things that those constructors construct to basically add information about placement or testing or other things. So we think about this as a compilation process where there's many passes that go on, and the first pass is what generates the functional model. And so you can imagine that the passes could either add information in or use information. So you might provide floor planning information for your chip through some common interfaces that basically help in that design process. Okay, the third thing is something that Vivian talked about this morning, is that if you view your constructor as something that takes a description in and produces an output, you've got it all wrong, because you always have to build the application for the accelerator, and that means that you have to basically change what that application does in order for it to run well on your accelerator. And that means that you need somebody who really understands or an expert at the application space to basically play in part of this process, because they're the only people who know how to cheat in the application space. But that means that this whole system has to be accessible and usable to somebody who's an application designer who's not an expert in hardware. So what you're trying to do is provide them the high-level feedback that they need to know in order to do that, but allow them to play at the high-level space. And again, we're trying to do that by having the input in Halide, but there are lots of other possibilities there. Okay, another opportunity. If you think about building a constructor that takes, let's say we have this high-level generator and we can take this application and we can generate the hardware out of it. The fact is nobody really wants that, because nobody wants a piece of hardware that does this application they put in. What they want is a piece of hardware that does applications like the application they put in, right? But they want the right to change the application a little later on and have that whole constructor and everything else work. Okay, the problem is that all the solutions that I've worked on and my team has worked on are always something that says, given an application, I get a result. That's not really what we want. Now, the way we're doing this in the Stanford AHA project is we're cheating. We have a CGRA, so we're optimizing the CGRA for that class of application. But if you put a different one in, we have an end-to-end system, we can still map it. But if you're building a more specialized accelerator, the problem is how do you get the specification for what that accelerator should do, because it is not the application that someone handed you. Okay, and that's another really interesting opportunity to look at if you're trying to work in this agile design space. Okay, the fifth opportunity is, as I think Dave, or I forget, somebody said, is like, agile design is all about reuse. And the fact is that if you're not reusing 95% or something of your code base, you're not doing agile design because you're trying to write too much code. So you're always building your system on top of some existing systems, and you're leveraging all that code. And if you're not doing that, you're not agile. If you think about what we're doing at Stanford, we're creating a whole new set of tools to use. And when I look out to my community, it seems like everybody else is constructing a whole new set of tools to use. Oops, we are not reusing a lot of tools, okay? And so to me, the biggest problem that we face in this whole agile thing is we haven't actually all agreed on what are some established tools that we're going to use. Everybody knows that they're doing things better than everybody else and they're doing their own stuff. I mean, I'm as guilty as everybody else, right? I'm just saying this is not the way to the Agile future. So we should think about that a little bit more. Okay, the next opportunity is about open source. And I think lots of people have talked about open source in various different ways. This is my particular take on open source. I think open source is really about commoditization of a function. When you open source something, what you're really saying is I am making the NRE costs, I am giving away the NRE costs. Okay? So, and why am I doing that? So I do this if I'm providing something that's essential for things that I need to build, but I do not think I have very much competitive advantage from that thing itself. It's the things I can layer on top of that thing, which is going to make me money. So what I'm trying to do is I'm trying to commoditize the base platform because the value added is the things I put on top of that. If you think about all the things that we're doing with the open source compilers and build frameworks and operating systems, I think it's all attempts from large companies to basically commoditize a base layer, which they need because it's very complicated and it's very important. Like none of Google would run without OSs on any of their platforms, but that's not where they're making their value. Okay, so it gives away NRE cost, and it does that in return for lower maintenance costs. So in that context, what does open source hardware look like? How are we going to make open source hardware in a place where it makes sense to give away the NRE costs for the hardware for lower maintenance or for that collection of things? And I think, I really want this solution. I really want this future, but I think figuring out how this actually works is important. And I will just point out that all the IP for vendors that are selling you this very expensive IP, they are all not making a ton of money. It is not like they're making money hand over fist, which means that those NRE costs that they're doing to support you are close to what you're paying them. So we got to do something different there because money can't be created. So if we're in balance now and we take something away, that's an issue, and I think that's important to think about. So in conclusion, I think Agile hardware is possible. I think we're doing it, we're on the road to do that at Stanford. It brings up a lot of really interesting research opportunities, and just because school A is doing it clearly doesn't mean that school B or C or you can't do it too. I think there's lots of opportunities here. But I will say, please don't fall into the many rat holes that are possible in this space because there are many, and many people have already fallen into them, so we should take advantage and avoid them when you can. Thank you all for your attention. So the question was, have I thought about the systems even in a broader context, in the context of distributed systems? And I will say that when I said systems initially, I was talking about in the systems that are used to the user. Okay, so what your question is completely consistent. So if I'm building a TPU, I have to think about how that TPU is going to fit within the Google data structure infrastructure, which is a large distributed system. So you're dead on. Personally, I am more worried about just moving from hardware to a system. When I get that, I will work up to the next level because I think there's enough challenges just like everything that gets produced today has a control processor and often has a Linux processor in it. How am I going to interact with that? How am I going to get, if I have a user space applications or non-protected applications and protected stuff, how do I basically cross those boundaries? There's a whole bunch of interesting things there. In large distributed systems, the protection boundaries are often different and there are other issues going on. My point was really you have to think about what the system application, so what is going to deliver the customer value, and you have to basically work and work from there. And for different applications, it looks different. Yeah.
You had mentioned everyone's building their own flows, and that it would be great if you could agree upon flows. Do you have any thoughts on which pieces are most
So the question is, I talked about everybody building their own flows, and do I have some opinion on what are the most important pieces? I think I don't want to standardize too soon, because actually the other truth in open source is nobody decreed that this was going to be an open source standard. There's lots of things that get put out, then people actually start using other people's stuff, and that is what becomes the open source standard. So I would suggest us to periodically look out to what other people have done, and maybe even go so far as to try it before deciding after you read a little thing that you're going to do it better. I mean, I think that would be a huge advantage. I will say there are certain parts of this process that I think there's commonality already when I look at all the different teams. So this intermediate representation that I'm talking about, everybody I've talked to has some data flow representation. And they're slightly different, but I don't know that they're that different. And if we could stabilize on that, then we don't have the n squared. Then it would make it easier for us to try different things, because we would have at least one common interface that we could plug into. So that's the most obvious thing that I say. Another big problem that's striking me is that using CAD tools, I think someone talked to, is just incredibly complicated in all the flows and everything else. And if we could just get some standard flows that actually work that we could use between different groups, that would be enormously helpful. And yes, they're all NDA'd, but we've all signed NDAs with the right people, so there should be a way to do that. Chris?
You mentioned formal a little bit, and so I think just getting testing to be more a central piece of open source hardware is the first step, but maybe you could talk more about the role of formal verification in open source hardware?
Yeah, so the question was about what's the role of formal validation or formal methods to open source hardware. I think one of the big problems that we have right now is that when someone delivers you something, you have no idea how it's been tested or whether it's working. And in software, you might think, okay, I'm going to try it, but you don't even do that in software. You basically use packages that a 1,000 or 1 million other people have used, so you're pretty sure it's going to be working. When someone gives you an IP block that they and their students constructed, you have no way of knowing that's true. So I think we need to do much better on the validation, and there has to be some way of standardized validating, or at least marking how it's been validated. The interesting thing about formal techniques is that formal techniques have become much more powerful and useful over the past decade. The ability of those tools to solve problems has grown dramatically. Now, they're exponential problems, so there's still a limitation, but they can be deployed on large numbers of things. But more importantly, formal is very useful for doing constrained random generation and stuff like that. If you have a formal spec, one of the problems you have, even if you have some sort of specification, is that you need to basically simulate that spec against the hardware. Well, the spec is not going to be accurate in all possible input cases because it's a spec and it doesn't actually care about things that are stupid to do. Okay, but if you put inputs in and you're basically doing random testing, you're going to run into these cases, and then it's going to mismatch, and you don't know what the problem is. So everybody in industry does what's called constrained random testing, which is they have constraints on the random test generation vectors and things like that. There are a lot of very useful formal techniques that you can do that are basically specs on interfaces or other things that can then be used for generating random vectors if I can't formally validate the whole thing. But even more importantly, if you put those formal things in, these are basically expect, require kinds of constraints. So if you have that, you might be able to formally prove something about it because you can limit what's the legal inputs. And so by putting it in, you help both into the test generation and in the formal validation. And the other thing is that there are very powerful techniques that are available today, which basically use symbolic analysis using these formal methods, where you can have sequences that should be equivalent, and you can ask the tool, are there any possible settings of these other variables that will make these two sequences not equivalent? So for an instruction set architecture, it's really easy. You put the same instruction stream in and you change the registers or something. And you say, are there any time these things aren't going to be the same? Okay, and what it will do is it will find if there's any case of page faults, misses or whatever that cause those two sequences not to return the same value and tell you. So there's lots of ways that formal techniques are very useful in terms of being very powerful test generations, and we need to incorporate that in the IP testing and make that part of the IP test library. And Clark Barrett and some other people at Stanford are working on issues like that. So, yes.
starting you guys out, like, do you have any ideas how can we reduce that maintenance cost or overcome that cost, like, even in competitive cities,
Yeah, so the question is about, I talked about open source is about giving away NRE for reduced maintenance costs, but there is still maintenance costs, and how do we basically pay that maintenance cost? Because people get bored with maintenance, right? And I think that's a really interesting question. The way that happens is that you have to have a large enough user base. So essentially, the reason open source software works is because the companies who use it spend a ton of money, or they pay a lot of engineers to maintain that source. Okay, and Google does it, and Facebook does it, and various other people who use the source. And so any one company isn't paying all that maintenance, but it's paid more by the community. The problem right now is we don't have anybody who uses our open source stuff that we put out. So there's nobody who's doing maintenance because nobody's using it, and then people graduate, and then it's not maintained, and then it's not very good, and then people think open source hardware is crap. So I think the only solution to this is that we actually have a community that starts really using, and maybe there's a smaller set of things, but it has to be a group of people who are using things and maintain it as they use it, because maintenance is a cost that has to be borne for anything that's going to have any longevity, and it's not cheap. So you're exactly right. So.